Hello and welcome to GeoProven, the Earth and Environmental Education Center of Provenance Geosciences in support of carbon negative water and energy. I'm Dr. John Hoagland. In the geosciences, I do a lot of mathematical modeling and teach quite a few math subjects. This video is about exponential growth, and it's Friday, March 20th as I record this, and Monday the 16th I was reading an article about the COVID-19 virus and the quarantine nationwide. I've just finished 5 days of quarantine myself, and saw a graph when I was reading Monday of the growth in the COVID-19 cases across the United States. And it looked like a perfect example of first order growth, exponential growth. So this video is titled Exponential Growth, an example of first order differential equation, its solution with the exponential function, and a fit to COVID-19 data. And this is the article that I was reading on Monday. Actually, by the time I saw it on Monday, I think it was only graphed to March 13th. You'll see this graph goes from February 20th to March 15th. I was looking at a graph on Monday morning of March 13th in Daily Costs newsletter that I received. By the time I got back to looking at the graph again that evening, Mark had published an update graphing it through March 15th in this article entitled "The United States Passes 4,500 Cases and People Are Beginning to Realize What's Coming." So Mark Sumner, Daily Costs, wrote this and came up with this graph. And I looked at that, like I said, with the data through March 13th, and now certainly with the additional data, 2 data points, that's definitely exponential growth. And I thought it'd be good to apply some math to this and learn about that. So the first thing I did was a reproduction of Mark's graph. I don't like tedium, don't like compiling numbers, especially if I try to read them off the graph. I did go looking at the Center for Disease Control and found numbers that were similar, but kind of wanted to get Mark's data. I sent him an email, and he graciously provided me his data in an email reply. So I thank Mark for that. Reproduced his graph here. My scaling is a little different, so my graph is a little bit scrunched up. Part of the reason for that is I have yet 3 more data points that Mark added to the graph when he replied to me for the 16th, 17th, and 18th. I don't have those graphed yet, but I will show you that later. So at first I reproduced the graph from the preceding slide with the data, and it shows the total number of cases in blue through time from, again, February 10th to March 18th. Each day's total number of cases. The bar chart down below in orange is the total number of new cases. And this is the thing with the exponential growth. The number of new cases grows each day, and it adds to the total, so the total grows. It's a function of the amount that's there increases the amount that it's growing. So not only is the total number of cases growing with time, the total number of new cases is growing with time. This is classic. We're not just adding a constant amount every day to the total. We're adding an ever-increasing amount to the total. And that's because the infection rate is a function of the number of people who are infected. And we express that rate relationship with a differential equation, the derivative of the total of the change, and that is in the total population with the change in time, is going to be some infection rate R times the total population size, the total infected population size. So as that infected population grows, it has a certain percentage of the overall population that it's going to infect and add to the total. That infection rate is a function of the number of interactions of infected people with a greater population, as well as the properties of the virus to create infection. So the biology of the virus and how virulent it is. It actually takes quite a bit of work in calculus proving that you can move differentials around at different sides of the equation like you can with algebra. It's okay as long as you keep track of things like the chain rule and various other rules in calculus that must be honored. But we're moving the population portion of the equation over to the left, the n terms, and we're moving the time term over by the rate. We then proceed to integrate this. Now the integration is the sum, remember, so we're summing the total number of cases from some initial time 0 to the final time that we're interested in solving. So the cases are going to grow from an initial number of case loads to the total that we're expecting at that time t. We expect to see a total number of cases n. So the limits on the integration are respective to n naught and t naught and n and t. And when we perform the integration, if you're familiar, the integral on the left is the natural log of n, and the integral on the right is just t. So we get, when we evaluate the limits on the integration, we get the natural log of n, what we're interested in at the final time t, minus the natural log of the initial population, that we started growing from, the initial infected population that we started growing from. And then we have the rate term times the final time minus the initial time. And we're going to call that final time and initial time the elapsed time. And the time elapsed is the time that we're solving as grown from the initial time t0. So restating the model, we have the natural log of n, which is the natural log of the total number of cases, minus the natural log of n naught, which is the total number of initial cases, is equal to the rate constant times t minus t naught, which is the elapsed time. So if we put the substitution for elapsed time in on the right, and then if we also recognize that the difference in logs is the same as the log of the quotient. So that looks like this. So the natural log of n minus the natural log of n naught becomes the natural log of n divided by n naught. And that's equal to the rate constant times the elapsed time. So now we apply the exponential function. Recall that the natural log system has a base called e. It's a number, 2.714 or something. Keeps going on, much like pi does, forever. The exponential function of x raises the base e to the power of x. So the best analogy I can give to that is that if you take the base 10 and raise it to the power of x, you'll get 10 to the x. Well, if I raise the base e to the power of x, I get e to the x. So I'm going to do that here. I'm going to take e and raise each side, the left and the right side. So I have e to the power of the natural log of n over n naught is equal to e to the power of RT. The base of a logarithm system raised to the power of the log of x returns x. So e to the natural log of n over n naught returns n over n naught. So it's e to the natural log of some x is x. The other side remains the same, e over RTE. And the final little bit of algebra here, n equals n naught e to the RTE. And this is now our model for exponential growth, starting from some initial value with e to the power of the rate constant times time. To make the model useful, we have to solve for that rate constant. If it's not given to us, we're going to get it from the data. So again, here's our model, let's back up a step. Let's look at the log, and we're going to now solve this for r. This was a form that we had it before we applied the e to both sides. And let's just solve that for r and see what we get. Rearranging, we get the rate constant is the natural log of n over n naught divided by the elapsed time. Now I'm going to take data for each of those variables on the right hand side, n and n naught, as well as the elapsed time, to come up with an r value. So I was looking at the graph, Mark's graph from daily costs, and I decided to take the value on March 1st and March 13th, which at the time was the last day that I saw plotted, was March 13th. So there's March 1st. That data point was 82 cases. And March 13th, that value was 2,276 cases. Now I'm just forcing the model through those 2 points. I could have picked any 2 points, I guess. The better way to do it would be to regress the data and find the best fitting r value, because r is much like a slope. Well, actually, if you were to plot this in log space, you would get a line, and you could in fact treat r as a slope, and you could regress the slope much like you do when you regress a line to data. You can get the best fit r. But I'm just forcing it through 2 points here. So again, we have that r is the natural log of the quotient n divided by n naught over te. Plugging in the numbers for March 1st, the t naught is 0, and the initial number of cases was 82. On March 13th, 12 days for time, and the number of cases is 2276. The elapsed time is 12 days between March 13th and March 1st. So plugging that in for r, I'll ultimately get a value of 0.276955. The r will have units of the inverse of days, because anything in the exponential function has to be dimensionless. So if you have time going in days, the r is in inverse days. You have to have the time expressed in days to use that value of the constant. So the final model then is the number of cases is going to be 82 e to that rate constant times time. When I do that, I have now fit the line, forced it between March 1st and March 13th, and I show it here in black. So the model, you can see on the in-between data points is fitting exceedingly well, almost exactly as expected for first-order exponential growth using that rate constant. If I extract the model or extrapolate the model, I can extrapolate it back to February 10th and forward to March 15th. And like I say, Mark provided some additional data points for the March 16th, 17th, and 18th. So here they are, except that I lied. I didn't provide the last two. This is actually the data with March 17th and 18th added on, the last 2 points way above the graph. So we're off the chart. The mathematical model is still in black. It still matches the point at the very end for March 18th. So here's our chart and here's our model, both indicating cases going off the chart. It's very difficult to intuitively think about geometric growth, exponential growth. Is there another way that we can think about this that might help us wrap our brains around what's happening here? And that would be the concept of double life. You're familiar with half-life, with radioactive decay. Decay follows the same math as this, only with a minus rather than a plus, which means a minus rate times time term in the exponent in the exponential function rather than a plus, and that causes decay that depends on the amount present. Well, this is growth that depends on the amount present, and so instead of half-life we can talk about double life. So what is the doubling time? How much time does it take for the case load to double? We can start with the original form of the equation and solve it for t, the elapsed time. Do that by performing the logarithm on both sides. Well, n divided by n naught, then take the logarithm of that. Take the logarithm of the other side, you're going to be left with RT. Run the R underneath and you solve for t, elapsed time. We're going to look at a special case of that elapsed time where the natural log n over n naught is 2. In other words, there's going to be 2, the doubling time from n naught to the next n is 2. We do that, we get t sub 2. It's a natural log of 2 over 1 divided by our rate term, which we got from the model. And we have a doubling time of 2.5 days. So every 2.5 days, the number of cases, COVID-19 cases, are doubling in the United States. So according to this model, the cases are doubling every 2.5 days. Will this continue? Well, the data point on March 18th, that is off of this chart, beyond the range of this chart, was 9,276 cases. And as I finished this video, Friday, March 20th, looked out on the CDC website. The number of U.S. cases is now 15,219. So it certainly looks like that trend is continuing. But will it continue indefinitely? Will it continue at this rate? The short answer is no. First order growth cannot be sustained in nature, and it's usually because other factors come in that limit the growth. Initially, the infection rate R is a constant, but in epidemiology it's a function of 2 components that become variable. The infection rate constant is a function of 2 components that become variable. The first is the number of encounters. That's the number of encounters of the uninfected population with the infected population, E. You can sort of consider that mixing. And the second component is the probability that each encounter will result in a new infection. So we can think of the growth constant as being the multiple of these 2 factors. We can affect these components. The first one, the encounters, is what we're doing right now. We're trying to lower the number of encounters by quarantining, social distancing, and practicing other forms of avoidances. And that lowers the encounters that we have with the infected population. Then as the immunity grows in the population, the probability of each infection decreases. Unfortunately, a significant portion of the population will either have to become infected or will have to be inoculated with some vaccine for this to go away. But the net result of lowering the encounters and lowering the probability is to lower the growth constant, which levels off the growth curve. So flattening the curve is certainly the goal, and we're doing that by lowering E, and that's the reason we are sheltering in place right now. Right now, we are having an exponential increase in the number of cases. Every 2.5 days they're doubling. And that's like the left side of this bell-shaped graph in solid purple here. That exponential growth, the tails, if you will, of the bell curve, on the growth side of it to the left side, that's the exponential growth curve. That's actually very easy to model. And then as the growth curve levels off, because we're either lowering the E or we're lowering the probability of infection, the epidemic will will peak and then will begin to decay away. And the question is what kind of shape do we want on that bell curve? Do we want an initial spike that then goes away, or do we want to spread these infections out over the next couple of months and with a lower total number of cases at any given time? Well, thanks for joining me. My goal has been to teach the mathematics of exponential growth, and there's more information about exponential growth and epidemiology, epidemics, at this video that I found, Exponential Growth and Epidemics. The person does a very good job in presenting why growth curves level off, so I recommend that video very much. And then a second article that was very elucidating, it's coronavirus. What is flattening the curve and will it work? And that's a bit about why we're sheltering in place right now. I should say that I'm Dr. Hoagland, but I'm not a medical doctor. So I'm just a mathematician and a geologist and natural phenomenon. So all I can recommend for you is that you stay safe, you stay separate, and you stay sterile. And come enjoy some of my other presentations. Thank you.